excited about this one? Okay. Fourth quiz. We will probably, depending on how many quizzes we take, I'm guessing we'll get 8 quizzes in, so we'll drop 3 or 4 of them. So if you haven't had a good quiz yet, it's probably time to do that. This one is a little bit bigger, as I said, kind of sums up all the stuff we've been talking about in the last chapter, which is an important chapter, being able to do these chemical reactions, chemical quantities, all of that. So this will be a big portion of the next exam, which will be in 2 weeks, right? 2 weeks from today. So please, please, please work on this. If you have been doing your homework, you've probably seen all this. All these problems were from the book. So all this stuff should have been somewhat familiar to you. All right, let's look at some balanced chemical equations and how we solve them, how we figure out what they are. The first one, we've got C4H8 and O2. What's happening there?
Combustion.
Yeah, combustion. How do you know? Right, because when we see hydrocarbons with oxygen, we know that's evidence of combustion. So what are the products of a combustion reaction? Yeah. So always water and carbon dioxide are the products in a combustion reaction. So we need to balance this. That means we've got to have 4 here, 4 here, 6. That's right. Does that work? Yeah. Okay. If you set up the atom inventory and did the balancing that way, that's great. But as you practice it more and more, you'll probably get a little faster at it to where you can kind of just go back and forth between the compounds and do it this way. Okay, ammonia reacts with hydrochloric acid to form ammonium chloride. So ammonia is given as NH3. We know hydrochloric acid is HCl. And ammonium chloride, that we may not know. That's a compound that we have to build. Now we should know that ammonium is an ion, NH4 plus from that list of ions. And chloride is Cl minus. So you've got the NH4 and Cl, one of each, cancels out the charges. And our final product is NH4Cl. Is that one balanced? That is balanced as is, right? All right, so what kind of a reaction is that? That's combination, right? You got 2 reactants, they simply combine together to form one product. And then finally, aluminum metal and iron 3 oxide react to form aluminum oxide and iron metal. So aluminum, if it's just a metal, that means it's by itself. Iron 3 oxide, we've got iron 3, which is iron 3 plus, and oxide, which is O2 minus. So if we want to make a compound from those 2 that has a neutral or 0 overall charge, that's going to look like that. On the other side, aluminum is always a +3 ion, and oxide is always 2 minus. So we've got a similar kind of compound to form there. And then the iron metal, which is just Fe. So what type of a reaction is that? That's a single replacement, yeah. Oh, and that's not balanced. How do we balance that? We need to balance that, right? So we need 2 of these, whoops, 2 of these, and 2 of those. That should do it. Okay, and then 2 of these chemical quantity type questions. One of them, you're given the equation, you just need to calculate the mass on the other side, the same way we did all those examples in class. And then the second one, we have to set up an equation and do it that way, as we've done before. So in this case, we've got 5.24 grams of the CaCN2, which I think might have been a typo in the book, I'm not sure. Maybe not. But anyway, this comes straight out of the homework from that chapter. Chapter, is that 7, right? Yeah, chapter 7. So we've got 5.24 grams CaCN2. Then we're going to go from grams, what's happening here, to moles. Then moles of this one to grams of the NH3, ammonia. Whoops, to moles. Yeah. And then finally, moles of NH3 to grams of NH3. Okay, so we've got to add up those masses. The mass, so calcium CN2, calcium is 40, C is 12, that's 52, and then N2, that's 28, so 52 and 28 is 80. If you did more decimal places, that's fine. I just didn't want to pull out a calculator. So then the equation tells us that we've got 2 of these for one of those. And then NH3, that's 14 plus 3 is 17. So our final total mass is 5.24 divided by 80 times 2 times 17.27 grams of NH3. Get something like that? Yeah, okay, good. So these things will keep coming up. Like we said, it's always the same kind of a problem. So once you get enough practice, once you've done a bunch of the book ones, you're not going to see any surprises there. It's always going to be like that. You can guarantee you're going to see these on the next exam. So if you're having trouble with these, work on it now. Otherwise, you're going to lose however many points on that next exam.
When is the next exam?
2 weeks, I believe, from today. Yeah. I think that's right. Check the schedule, but I think it's 2 weeks from today. What? 27th, is that right? I think that's right, yeah, because we've got a lab today, and then lab next week, and then the exam. All right, and finally, this one we have to set up an equation, so we have to know the products as well as balance it. So hydrogen and oxygen gases, when they react, what do they form? Water. So is that balanced? It's not. This is one of the ones we did in class, so we've got to put a 2 here and a 2 here to balance it. All right. Also, to get this balanced properly, we had to remember that hydrogen and oxygen gases are diatomic gases, meaning they're H2 and O2, not H and O. And we need to know that they form water when they react. So now we have a balanced equation. We don't have to go all the way from grams. We can go from moles. So we've got 2.0 moles of H2. And then our equation tells us that the relationship between moles of H2 and moles of O2 is 2 to 1. So we need 1 mole of oxygen for 2 moles of hydrogen. And you could probably just have seen that from the equation. You may not even have to calculate that out. So that's how you do a thing like this. Now, of course, you need to have the correct balanced equation to get these ratios right. So these types of problems rely on some previous information because you need to get all the steps ready. So make sure, as you're getting ready for the exam, make sure that you can write compounds from names, because that's going to continue to be important. You'll notice here on these 2 problems, I didn't give you any super complicated writing compounds from names, ionic stuff or whatever. So that will definitely come up. So make sure you can write compounds from names, make sure you can write and balance chemical equations, and make sure you can calculate these quantities. That will be the bulk of the next exam. And that was quiz 4. Questions? Okay. All right, let's move on then. Our next chapter is a little bit weird because we're not really going to follow the book on this one. We're going to talk about gases. And when I say we're not really going to follow the book focuses on calculations involving gases. How to calculate these different quantities of gases, these different issues with gases. And we're going to skip the calculations. So we're going to focus on just the descriptive part of gases. In other words, talking about them. What happens when we do this? What happens when we do this? That kind of thing. So that said, there's not really a lot of homework to do in this book. This is the one part of this class that's really more like you just have to kind of learn this stuff from your notes, and you're not really going to practice problems in this way. So just be aware of that we're not really, if you're looking through the book, we're not doing all of the math type gas problems that you'll see in that chapter. We're just talking more conceptually about it. All right, so who knows about gases? We know things about gases? What is a gas? Nobody knows what gas is? Have you heard that word gas before? Okay. I figured, I mean, we just talked about phase changes, so you must know some things about gases. What makes something a gas? What is it that makes, or let's define it in relation to other phases. So what is different about a gas compared to a liquid or a solid? It's, well, okay, that's a lot of stuff. So who wants to try? Go ahead, I guess it's like
the particles move faster.
The particles move faster?
Like molecules.
As we'll see, that's not always necessarily the case. But yeah, there is some more distance that they cover when they move, for sure. What else about gases? Heard other people saying some stuff. Did you have something?
The forces.
Some of them you can't see, but the forces are weak, so they're not really attracting each other, which is why they're really just individual molecules. Yeah. Anything else?
Don't have volume.
Yeah, that's really how we differentiate gases from the other states, is that we say that gases have no fixed shape or volume. If you take a 600 milliliter beaker, this beaker right now is filled with 600 milliliters of gas. So whatever amount of gas is in there, however many grams of air is actually in there, it's filling 600 milliliters. If a gas always takes the shape of its container, then how do we figure out how much gas we have? It's kind of a tricky thing to think about, right? Because if the gas is always going to fit in here, how would you know if you put more gas in it? Let's say we did this. Let's say I was able to kind of seal this thing up, and I went over to a gas nozzle here. I'm not going to fill it up with flammable gas, but let's say that I were to do that and kind of hold it, and I put more gas in it. What would happen inside there? If I didn't change the volume, but I put more gas in, what would happen?
The pressure is.
Yeah, the pressure would increase. Does that make sense? You put more gas in here, if you just blew in there or something, the pressure would increase. So pressure is this idea that's really important to measuring how much gas we have, because the volume stays the same. And weighing it is sometimes tricky because some gases are lighter than air, and since weighing it is really a force based on gravity, you imagine if you have a helium balloon, you can't just put it on a balance and figure out how much helium is in there because it would just go up. It actually has a negative weight. So we need to look at something called pressure, and that's a quantity that we haven't really worked with before, so let's talk about it. What is pressure? Have you heard that term before? It's a fairly common word. What is it by definition? What is it truly a measurement of? What does pressure measure? Well, force is a different quantity. So what is special about pressure that is different from force? Pressure is a force over an area. So a force that's distributed over a particular area. Which means that the pressure can change without changing the force. So for example, we all exert a force on the Earth, right? Because of gravity, well, we technically, with the Earth and us, exert forces on each other, but we could think of it as I'm exerting a force on the ground simply by having mass that has gravity being pushed onto the ground. So how could I exert greater pressure onto the ground if I can't change my force, can't change my weight? What could I do to increase the amount of pressure that I put onto the ground?
Jump. You can jump.
Actually, you could jump. Jumping actually is increasing your force because now you have more acceleration from gravity. So what if I'm just standing here? How can I stand here in a way that increases the pressure that I put onto the ground? What? Okay, but that's, again, increasing my force because now I have greater mass. Now I have greater weight. What if I'm just standing here like this? What can I do? How can I have greater pressure onto the ground? Well, I could do something with my feet. I could stand on one foot. If pressure is a force divided by an area, there's a certain area that my feet are taking up, and my entire force is distributed on that area. If I pick my foot up, then I have a greater pressure. Sorry? Yeah, so if I were sitting, it would be a lower pressure, right? Because now my pressure is spread out over a greater area, or if I laid down on the ground. Things like that. So it depends the area that's being pushed against is part of pressure. This isn't something that is a huge issue for me, but if you wear shoes with really small heels, like small high heels, anybody ever tried that? It's tricky. I wouldn't recommend it. But if you go walking in like a field, what happens? Anybody ever had this issue? Like an outdoor wedding or something?
Yeah.
You like sink into the ground? Yeah. And what's happening? Like you haven't gained any weight. You know, you probably maybe feel heavier, but you are actually still the same. But because you've got these thin little heels, all of that force of your body is being spread over that very tiny area. And the pressure is greater, and therefore you push through the ground. So if you wore giant clown shoes, you know, that wouldn't be an issue. And that's why you might wear something like snowshoes, and you can walk on top of the snow because it distributes your force over a greater area. So pressure is the force over an area, which means pressure units are always going to be something about that force over the area. Does anybody know a unit of pressure? What is a measurement of pressure? What is a unit that we use to measure pressure?
PSI.
PSI is one. Have you heard of that one? What does PSI stand for? Yeah, pounds per square inch. And the way we would write that, like we write our other units, would be pounds divided by inches squared. Inches squared is the area, the amount of space, or the amount of area, and pounds is the force on that area. So pounds per square inch, yeah, that's a measure of pressure. What do we use that pressure measurement usually? Where do we see that usually? Tires, sure. Everybody check your tire pressure recently? Or I guess a lot of cars have the automatic thingies now, so people don't have to check them as much. But if you don't have one of those automatic thingies, make sure you check your tire pressure. Where else do we see that?
Like soccer balls.
Yeah, I mean, inflating air, that kind of stuff. We'll also see it on things like oxygen tanks. You know, if you have those gauges on the oxygen tanks or on other types of gas tanks. Pressure is a good measurement of how much gas you actually have. Because if you have a fixed volume, you know, it's like a gas cylinder, as you put more gas in that cylinder, the pressure goes up. And so that's often how we measure how much gas we have, is by looking at the pressure. So when you look at, say, an oxygen tank in a hospital, and you want to know how much is left, how much oxygen is left, you look at the little pressure gauge, and it tells you how much, you know, how great the pressure is. As the pressure goes down, that means that the oxygen level is going down. So you can use pressure to figure out how much stuff is there. Now, do you think we'll use pounds per square inch a lot in this class as our measurement of pressure?
Yeah.
Probably not. Why not?
Another question?
Well, we usually don't use the English units for stuff. We usually stick with more metric units. So there are a couple of units that we use more commonly. One is this one. Have you ever seen this unit before? If you work in healthcare, you might recognize it. Yeah, this is millimeters of mercury. Where do we see that unit? Blood pressure, right, is where you may have seen it before. It's actually a really common unit in science, but it's sort of a weird unit. Why would millimeters of mercury have anything to do with pressure? It looks like a distance, millimeters, And why does it have something to do with this element mercury? Does anybody know where this comes from? Why do we call it millimeters of mercury? I'll tell you. So it comes from this old instrument. And what you can do is take a container and fill it up with liquid mercury. Don't actually do this, by the way. Mercury is poisonous, and it has a poisonous vapor. So even if you're not like eating it, it can still hurt you. That's why we don't use mercury in the lab. But if you took a bucket and fill it with mercury, and you evacuate a tube and put it upside down in the mercury. So you take all the air out of a tube and you put it down into the mercury. What do you think happens?
Separate. Surrounds the tube.
Yeah.
Mercury rises.
Yeah. The mercury is going to go up the tube because the tube doesn't have any air in it. It's got a vacuum. It's like if you sucked all the air out of it and then put it in there, the mercury would go up the tube a certain amount. So the mercury goes up the tube up to, let's say, here, to a certain level. What is pushing the mercury up that tube in this situation? Why does the mercury go up the tube? Why doesn't it just stay at the same level with a tube in it? Any idea?
Maybe because gravity is pushing down on the mercury.
Close, yeah. It's not exactly gravity. It's the atmosphere, the gravity of the atmosphere pushing down on the mercury. Remember, we don't think of the air as really being anything, but it's actually this huge mass of air that through gravity is pushing down onto the Earth. And so if you set up a system like this, the atmosphere is pushing down on the mercury and pushing it up into that tube that is evacuated. So the amount of distance that it gets pushed up that tube, that's that millimeters of mercury. If you counted that distance in millimeters, it would go 760 millimeters up that tube, depending on the size of the tube and so forth. So that's called atmospheric pressure. So 760 millimeters of mercury is what we call atmospheric pressure at sea level. So at sea level, that's how much up that tube the atmosphere would push the mercury. Now we usually just use it as a unit, and we often call it either millimeters of mercury or its related unit torr, which comes from the fact that this particular instrument is called a Torricelli barometer. Another unit then that we can derive from this is the atmosphere, the ATM. The atmosphere is simply the amount of pressure that the atmosphere exerts on the Earth at sea level. Any other pressure units that you know about?
I don't know, what they always talk about barometric pressure.
Yeah, barometric pressure. What's that? So let's take a look at that. This site has kind of a neat way of graphing weather. So we look at this big graph of this weather forecast. This is kind of a cool graphic because it really has a lot of information in one thing. You see like pretty quickly a snapshot of what the weather's going to do. This red line is the oscillating temperatures over time. So you can see during the day it gets hotter, and then at night it gets colder, and then during the day it gets hotter again, and so on. Looks like we got some chilly weather coming up here. And then down on this one, you've got this black line, which is the pressure, the barometric pressure in inches. So what do you think that inches means? If pressure is a force over an area, how could a pressure be inches? Any ideas? Yeah, weird. It's actually the same thing as the millimeters thing. So that's inches of mercury, which is related to the millimeters of mercury, the same type of unit, but in the English system. So in barometric pressure, we use inches of mercury. And so you can see atmospheric pressure is somewhere around 29.9 inches of mercury, which is about here. So if we have higher pressure, that's usually evidence of fairer weather, and lower pressure is usually evidence of more overcast or rainy weather. The light blue bars back here are the chance of rain. So you can see as the pressure goes down, the chance of rain goes up. And then you can also see the wind speed down here. Shows you both the direction and the speed. So kind of a nice picture of what it's going to be like around here for the next few days. Yeah, so we've got inches of mercury, which is similar to millimeters of mercury. There's one more, and you don't have to know these numbers. I would know this one. That's an important number to know. Yeah, there's another one called the Pascal, which is the more technical metric unit. It's a much smaller unit. So as you can see, it's actually 101 kilopascals, gets us in that atmosphere range. You don't have to know that number, but sometimes that one will come up. If we need to convert among different temperature scales, we can do that using the same conversion type factors that we've done all along, just using these types of numbers. So I would give you those numbers if you need them. All right, so that's how we measure pressure, and pressure is how we measure the amount of the gas that we have. So the next part is talking about how the different measurements in the ways that we can measure gases are interrelated. So we're going to look at pressure and volume, volume and temperature, and a couple other ones. But I think I'm going to stop there because really this is supposed to be for Thursday, so we're a little ahead of schedule. So for the last 15 minutes or so, do you have questions about lab or other things that you have concerns about? If you have anything, let me know. Otherwise, you can work on pre-labs or whatever, or just get some lunch before lab. So we'll start up at lab right at 2, and I've got some fun gas demonstrations to show you today.